Hi, I'm Bella Moore.
And I'm Erick Vega.
On today's news segment, we're going to be going over medications. We have a couple focus questions asked by our viewers. Our first question is, how do acids and bases play a role in the effectiveness and absorption of medications? I'll let my friend Erick take it away. Action.
Hi guys, I'm Erick. Different parts of your body have different pH levels. They can be acidic or basic. A medicine must be the right chemical form to dissolve and to be absorbed into your body. An acidic drug dissolves better in acidic environments, like your stomach or other organs that might be more acidic, while basic drugs dissolve better in basic environments, like the small intestine, or also some other organs that are more basic. If a drug isn't dissolved, it can't enter the bloodstream, so pH affects how the medicine works.
Hey Erick, what's the difference between an active ingredient and an inactive ingredient in medicine, and why are they both important?
Question. Well, the active ingredient is the chemical that actually treats the condition, like reduces pain, kills bacteria, lowers fever, etc. The inactive ingredient helps the drug work properly but doesn't do anything. For example, fillers, colorings, flavoring, stabilizer. They both are very important in the medicine though. Inactive ingredients control how fast the drug dissolves, how it tastes, and how your body absorbs it. So the active ingredient works correctly. So the active ingredient does all the work, well, the inactive ingredient is just their flavoring, color, stuff like that.
So, like, an active ingredient would be the medication inside the pill, and the coating around it would be an inactive ingredient?
Now you're getting it.
Oh, good.
Oh, Bella, all this talk about medicine gives me some questions of my own. For example, how do buffers help maintain stability and control pH?
That's a great question, Erick. Buffer is a chemical system that prevents big pH changes in your body. In liquid medications, buffers keep the pH stable so the drug doesn't break down too fast, or prevents irritation in the body, like your eye drops. They must add, like, they gotta match the pH of your eye, so it doesn't mess up your eye. In the body, buffers, like the bicarbonate system, keep the blood pH safe around 7.4 and help medications stay in the correct form so they can work.
Wow, that really makes sense. So like you said, like eye drops must match the pH of your eyes to work.
Yes.
Thank you, Bella.
Of course.
Action.
I've heard about this thing called catalysts and enzymes, and they're in drug metabolism.
Oh, I know all about those. Don't worry. Well, inside your body, catalysts speed up chemical reactions. Enzymes, which are natural catalysts, break down the drugs in the liver. This changes them into forms of your body can use or remove. They decide how quickly the drug is broken down, how long it stays, or whether or not it becomes more or less useful.
It's really interesting.
Yeah. Well, actually, while on the topic of questions, I have a few more. How does bonding affect solubility in the liver?
It's a great question, Erick. Well, chemical bonds change how a drug dissolves and moves throughout your body. An ionic bond dissolves easily in water, and it's great for bloodstream travel. Covalent bonds are strong and stable. They're good for targeted action for, like, headache medicine or something like that. Hydrogen bonds help the drug interact with water, proteins, or cell surfaces.
Wow, that makes so much sense.
Now that I know about soluble things, I know that medicine has to dissolve either in fats or water or something like that. So what's the difference between lipid-soluble and water-soluble matters?
Great question. But before I answer, I have to clear up a few things. First of all, blood is made mostly of water, and the cell membrane is made of fat. Water-soluble drugs travel well in the blood because, like I said, it is made mostly of water. And they leave the body quicker when you urinate or when you go to the bathroom.
Right.
Lipids, fat, soluble drugs, can pass through the cell membrane, which again is made of fat. They can enter the brain more easily and they stay in the body longer. They're stored in the fat tissue instead of being through your urinary system. A drug's solubility controls how it travels, where it gets there, and how long it takes. So while water-soluble drugs work faster but come out quicker, lipids stay in your body for longer, but get to your brain more easily.
So cool.
Yeah. Well, speaking of that,
Are you okay? Do you need some ibuprofen?
How do pain relievers like ibuprofen and Advil work?
Great question, Erick. They block enzymes called COX1 and COX2. These enzymes produce prostaglandins, chemicals that cause pain, fever, or inflammation. By stopping prostaglandin, medicines reduce all three. Aspirin permanently disables the enzyme, and ibuprofen temporarily blocks it. Would you like some?
please. Thank you for the ibuprofen, Bella.
Of course. Don't you think that's a little bit too much?
I was just trying to. Why must Drug doesn't even control it.
Eric, too much can have dangerous side effects.
Like what?
It can affect multiple organs. It can give you headaches, it can give you diarrhea, it can give you a lot of symptoms. Some aren't great, some of them are very dangerous. And then too little of a drug might just not work.
Speaking of, where's the vaccines?
Ew, stinky.
Half-life is how long it takes for half of the drug to leave your body. A drug with a long half-life requires fewer doses, while a short half-life requires it to be taken more often.
Right.
Bioavailability is simply how much of the drug reaches your bloodstream. Some drugs lose part of their dose in your stomach and liver, so only a fraction comes out. So while you may take a medicine that's 250 milligrams, only a fraction of that might be reaching your actual body or wherever it hurts. Both decide how much you take and how often you take it, but they still serve different purposes.
That makes sense.
Well, my last question of the day.
Finally!
How do antibiotics interact with bacteria, and why don't they work on viruses?
Well, Eric, antibiotics target specific bacterial structures like cell walls, protein-making machinery, and DNA-copying enzymes. These structures don't exist in viruses. Like we learned in biology,
Viruses are not alive.
so antibiotics have nothing to attack. Viruses use your own cells to reproduce, so an antibiotic can't reach them without harming you.
That makes so much sense. So bacteria uses its own cells in its own body to reproduce, while viruses uses your body and your cells to reproduce. Thank you so much.
Of course! Hi, I'm Bella Moore. Hi, I'm Bella Moore.
Nope, it takes a second.
Hi, I'm Bella Moore.
You saw my hand.
Hi.
Bella.